Learn like a pro.
So today, we're going to become architects of the invisible. Yeah, you heard me right. We're learning to draw the blueprints for the forces that run everything, from that little shock of static electricity to the smartphone you're holding. We are diving deep into the world of electrostatics. All right, so let's just get right to the heart of it. The big question for this whole explainer is this. If a force is completely invisible, how on earth do you draw a map of it? How do you chart its strength, its direction? That's exactly what we're going to figure out. You know, every great blueprint starts with a parts list, right? And for electrostatics, that means we first have to understand the fundamental players in this game. These are the building blocks of every single electrical interaction in the entire universe. And here they are. It all starts here, inside the atom. You've got your positive protons and your neutral neutrons packed in the middle, and then you have these negative electrons zipping around them. And really, it's just the push and pull between these positive and negative charges that gets this whole story started. And look, this isn't just some vague concept of positive or negative. It's precise. Every single piece in our blueprint has a specific value. And that number you see, that's the fundamental unit of charge, the coulomb. Yeah, it's an incredibly tiny number, but it's this exact, measurable quantity that lets us build and predict everything else. It's the bedrock. And these little guys, they follow two super simple, completely non-negotiable rules. Think of it like the most basic code in the universe. Rule 1, like charges, so positive and positive or negative and negative, they always push each other apart. They repel. And rule 2, unlike charges, a positive and a negative, they will always pull towards each other. They attract. That's it. Simple, powerful, and it happens every single time. Okay, so we've got our players, and we know their rules of engagement. Now it's time to map out the stage they perform on, this invisible arena of force we call the electric field. So what exactly is an electric field? Well, you can think of it like an aura, a region of influence that surrounds any charged particle. If you drop another charge into this space, it's going to feel a force, a push or a pull. It's the invisible medium that lets these forces travel and interact. Which, of course, brings us right back to our big problem. If this entire arena is invisible, how in the world do we map it? It seems impossible, right? Well, physicists came up with a really, really clever little trick to make the invisible visible. Here's the trick. To map the field around this big positive charge, we imagine a tiny little positive test charge. Just think of it as our pen, okay? It's the tool we're going to use to draw our blueprint. Okay, so now we take our little pen, our positive test charge, and we just place it in the field. And what happens? Well, we know the rule, right? Like charges repel. So our tiny test charge immediately feels a push straight away from that bigger source charge. And there it is. That's the big aha moment. The path that our little test charge takes, that is the field line. We just trace where it would go, and boom, suddenly that invisible force has a visible line, a direction, right there on our map. All right, so we've got our magic pen, but just like any language, there are rules. There's a visual grammar to these field lines, and it's actually just 3 simple laws that tell you exactly how to read and draw these blueprints. Okay, here are the 3 big rules. Rule number 1, direction. It's simple. The arrows always point away from positive charges and always point towards negative charges. Rule 2, integrity. Field lines can never, ever cross each other. I mean, think about it. A charge can't be pushed in 2 different directions at the exact same time. It just doesn't make sense. And finally, rule 3, intensity. This one's key. The closer the lines are packed together, the stronger the force. Where they're spread out, the force is weaker. And this diagram? It's perfect. It shows all 3 rules in action at once. First, look at the arrows. They're all flowing from the positive charge on the left to the negative charge on the right. See? Rule 1. Next, notice how the lines curve and bend, but not a single one crosses another. That's rule 2. And finally, look at the area right between the charges. See how packed and dense the lines are? That's a super strong field. But way out at the top and bottom, where they're spread far apart, that's a much weaker area. It's a complete visual language. Okay, theory is great and all, but let's put this stuff to the test. Let's see how these blueprints actually predict what happens in the real world. We're going to walk through a quick little story, the case of 3 charged spheres. This is where all our rules come together. So let's meet our first 2 players. On the left, we've got sphere X. It's positive, and you can see its field lines are pointing outwards, exactly like the rules say they should. And on the right, we've got sphere Y. It's negative. And sure enough, its field lines are all pointing inwards. Now, watch what happens when we bring them close together. Whoa! Look at how their fields connect. The lines just surge from the positive sphere X straight over to the negative sphere Y, creating this really dense, powerful field right between them. And the physical result of that map? The spheres get pulled together. That's attraction, perfectly predicted by our drawing. So, everything's stable. They're attracted to each other. But what happens if we throw a wrench in the works? What if a new third charge enters the system? Can our blueprint still tell us what's going to happen? And here it comes, sphere Z. Now, the key information here is that it contains only protons, which means it has a net positive charge. So what happens when we bring it near our other positive sphere, sphere X? Look at that. The field lines bend away from each other, like they can't stand to be near one another. They're showing this powerful repulsive force. And the result? The spheres are literally pushed apart. Just like our first rule said, like charges repel. It works. And just to wrap this up, check out what happens when you engineer a system perfectly. Here, between these two parallel charged plates, you get a beautiful, uniform electric field. The lines are perfectly straight, perfectly parallel, and evenly spaced. This isn't just a pretty picture. This is the kind of controlled, predictable system that engineers use to build amazing technology, like particle accelerators. It's electrical geometry in its purest form. So we started with a simple question, right? How do you map an invisible force? And the answer, it turns out, is that we draw a blueprint. We use a visual language of lines and arrows that can predict with incredible accuracy how charged objects are going to behave and move. You see, these aren't just some abstract doodles on a page. They are the actual blueprints for how matter moves at its most fundamental level. And it kind of makes you wonder, what other invisible blueprints are out there shaping our entire world, just waiting for us to figure out how to draw them?